So thank you very much to the organizers for inviting me to speak at this very nice conference. I also wanted to thank Kobe for organizing the very illuminating and important symposium yesterday for those of you who attended that. So I'm going to talk today about some work that's based on work done with these collaborators, Kyriakos Papadimos, my student Sudeep Ghosh at ICTS, Shavik Banerjee, who's a postdoc at Uppsala, and Jan Willem Bryan, who's a student at Groningen, and it's based on some set of papers we've written over the past year. So let me just try and give you a summary of what I'm going to say. So I think it's generally accepted, everyone would agree, that quantum gravity is not an exactly local theory. So for example, if you try and take two operators and you separate them by the Planck scale, we don't have a good way to make sense of that, and so we don't know what this commutator might be, even though you would expect it to vanish in a local quantum field theory. What I'm going to try and say today is that at least for some observables, these non-local effects are spread out over macroscopic distance scales. And the observables for which this happens are observables which have correlation functions which have a very large number of insertions. And the reason I'm going to claim this happens is because when you look at the algebra of local operators in gravity, this algebra of local operators satisfies certain very complicated polynomial constraints in that it might be that you can write a local operator at one time and at one point as a very complicated polynomial of a very large number of local operators which are localized at space-like separated points. And this idea is inspired by black hole complementarity. So in the course of this talk, I'll refer to this notion of polynomial constraints as complementarity. And if you accept that this is correct, then I'll try and convince you that this has rather significant implications for some versions of the information paradox. So some of you might think that these are strong statements. So the first thing I'd like to do in this talk is try and give you an example of how this version of complementarity can be realized in at least one example where we think we understand everything, and that's just empty anti-de Sitter space. And one of the lessons we learn from empty anti-de Sitter space is that these non-local effects, or this version of complementarity, is tied to the breakdown of perturbation theory, and so I'll try and describe that. And motivated by that, I'll then study the behavior of string perturbation theory for many external particles, and then I'll try and tell you about the implications of these results for the information paradox. Okay, so as I said, the first thing I want to do, just to have an example that we understand well and that will teach us something, is I want to tell you that this idea of complementarity can be realized just in empty global anti-de Sitter space. So here is the setup. Just think of global anti-de Sitter space. And in this global, it's empty, there's nothing in this ADS. And in this global anti-de Sitter space, I want to consider a time band of some length t on the boundary of anti-de Sitter space. And this time band is such that its length is shorter than the light crossing time of ADS. And if you have this setup, then you can see that it divides the bulk of anti-de Sitter space into two regions. One of them you might call the causal wedge of this band. And then there is an entire space-like diamond in the center of ADS, which is space-like to all of these points on the band. And now if you use the standard HKLL construction, then it's very easy to map simple operators that live in this causal wedge to simple operators, simple generalized free field operators that live in this time band. But what I'm going to try and show you is that if you're allowed to use complicated polynomials, then you can also map operators that live inside this diamond to operators that live inside this causal wedge or in this time band, even though these guys are space-like separated. Okay, so that's the result I want to reach. So here's how we do it. It's actually quite simple, and it isn't so surprising. So we take the operator in the middle of ADS, which I'll call phi of 0 for simplicity, and you just expand it out in a complete basis of states, where these C and M's are some C number coefficients that you can obtain by solving the wave equation or by using the HKLL construction. And then the first thing we do is you can write every state that appears in this expansion using the Reeh-Schlieder theorem as the action of a simple operator that lives on this causal wedge acting on the global ADS vacuum. Okay, so this is, you can think of it as just a Reeh-Schlieder theorem applied to the vacuum of global ADS. And these operators are written as xn, but if you open our paper, you can find explicit expressions for what these operators xn are. So far, there was nothing special. You know, what I said previously would hold in any quantum field theory. But there is something special about gravity. And what's special about gravity is that when you look at the projector on the vacuum, this projector on the vacuum can be thought of as a limit of an exponential of the Hamiltonian. And what's special about gravity is that the Hamiltonian in a gravitational theory in ADS is a boundary term. And therefore, this projector on the vacuum can be thought of as an operator in this causal wedge because it lives right next to the boundary. Okay? In fact, you don't even have to think of this very complicated exponential. You can take this exponential and expand it out in a finite polynomial. You can choose this value of alpha to be large enough, and it's not hard to persuade yourself that if you choose this alpha to be log n and take this polynomial to be of order n, in fact, with this choice of alpha you need n log n terms, then this projector, this polynomial approximates this projector very well as long as you don't insert it in states with energy larger than n. Okay? So now this is something that's very special to gravity and would not happen in the absence of gravity. So now if you put these formulas together, you just combine the effect of the Reeh-Schlieder theorem and the fact that this, this vacuum projector in the middle can be approximated by this polynomial, you end up with a rather explicit formula. As I said, you can make it more explicit by looking at what the forms of these xn's are, that says that this operator in the middle of anti-de Sitter space can literally be written as a very complicated polynomial of operators that live in this causal wedge C. And as I said, these are terms that come from the Reeh-Schlieder theorem, and this came from approximating an exponential to the Hamiltonian. So this is an example of the kinds of constraints that I was talking about, where you can sometimes really write an operator on one space-like slice in terms of operators that are elsewhere. And of course, this completely violates any notion of locality that we have. But it's important to recognize that these operators do obey locality to a very good approximation if you insert them inside two-point functions. If you take this guy and you insert it inside two-point or three-point or low-point functions, you wouldn't see any sign of the fact that it was really a very complicated polynomial that was made up of something that was totally different. So this is an example of the idea of complementarity that I was going to mention, and it will inform the rest of the discussion. Okay, so now what is it that allowed this kind of magic to happen? If you think about it a little bit, you'll see that the root of this non-locality is really the bulk Gauss law. Okay? And it's the bulk Gauss law that already tells you that in any theory of gravity, you don't have exactly local gauge invariant operators, and any operator that you define has to have some non-trivial commutator with the Hamiltonian, even though the Hamiltonian is defined at the same time slice. But it's important to recognize that these Gauss law commutators are actually small in some natural norm, and one way to see that is to look at the commutators between canonically normalized fields. So H is actually a large operator, but if you take the metric fluctuation and you normalize it canonically, and then you look at this commutator, you see that it's suppressed by a factor of 1 over n. But of course, in the construction that I showed you, these non-local effects were order 1. And the reason this happens is because these 1 over n effects can get enhanced to order 1 effects by the breakdown of 1 over n perturbation theory. So it was very important that the polynomial I showed you previously had of order n terms. Okay? So there are two effects I want to emphasize. One of them is the Gauss law, and the other is the breakdown of 1 over n perturbation theory. Now, you might wonder if the same kind of thing happens in flat space. And of course, it's true that the Hamiltonian is a boundary term even in flat space. This is something we knew from the time of ADM, a very, very long time back. And you can check, in fact, that the fact that you have this Gauss law and the Hamiltonian is a boundary term leads to commutators, but they're commutators between, non-local commutators between operators that in at least one example were computed by Donnelly and Giddings. And it's not very surprising that just like commutators in ADS were suppressed by a factor of 1 over n, you look at a configuration of operators and look at these non-local commutators, and they're suppressed by a power of E by m Planck, where E is some measure of the energy of this configuration of operators. So that makes you think, and this is suggestive, there's of course not a proof, it's suggestive that you might wonder whether if you were to combine the fact that there's a Gauss law with the breakdown of gravitational perturbation theory, whether that might lead to similar kinds of macroscopic non-local effects, even in flat space of the kind that you saw in ADS. Now, if you think about it a little bit more, this relationship between the loss of locality and the perturbative breakdown in gravity is also rather natural from the path integral point of view. You might have asked, why is it that the world around us is approximately local, even though the path integral sums over all metrics with given asymptotic boundary conditions? And the answer is very simple. It's the fact that for simple observables that we measure, this path integral is dominated by a saddle point. And the saddle point lets you define a background metric. And when you speak of locality, you're speaking of locality with respect to this metric. Of course, if perturbation theory breaks down, that's a sign that the saddle point approximation is no longer valid, and therefore your notion of locality might change. So it's not surprising that there's a relationship between these two phenomena, at least in some cases. Okay, so this is at least a motivation. It's not, as I said, a watertight argument, but it's at least a motivation that makes it interesting to study the behavior of gravitational perturbation theory for many external particles. And so that's what I'm going to do next. I want to study the behavior of string perturbation theory when you take the number of external particles to be very large. And what I'll try and convince you over the next few minutes is that it is indeed true that string perturbation theory breaks down if you take the number of external particles to be very large, but take the energy per particle to be small. Okay. So before I start, let me just try and tell you what the result is. So we consider some limit where the string and Planck scale are very widely separated, so G string is very small. And then we take a limit where the energy per particle actually scales like 1 by n to the power gamma in string units, but this gamma can't be too large, so the energy per particle can't drop off too fast as you take n to be large, but it can go to 0 as you take n to be large. Okay? And then the claim is that string perturbation theory breaks down at least at a value of n, that's some inverse power of the string coupling constant, or if you prefer to think in terms of Planck units, that's simply m Planck by this energy per particle raised to the power d minus 2 in these space-time dimensions. And let me emphasize that this is, in a sense, an extreme bound for when string perturbation theory might break down. It's possible that string perturbation theory breaks down earlier, but I'm going to claim that it breaks down at least at this value of n. So the way we show this is as follows. It's actually a rather simple argument that relies on simple unitarity bounds. So if you just use the optical theorem and then demand that loop amplitudes be smaller than tree amplitudes, you get a simple bound on how fast tree amplitudes can grow. And this is the bound. It's a statement that the square of the tree amplitude integrated to the final phase space is smaller than the tree amplitude itself. And then I'm going to argue next that string tree amplitudes grow like the appropriate power of G string into n factorial. And it's not difficult to check that if this behavior is really correct, that this inequality is violated at this value of n. You might wonder where the factors of E come from. They come from the volume of phase space that sits here. Okay? So it's not hard to check that if this is correct, then this inequality that I mentioned holds. And so what I want to do next is persuade you that string amplitudes for large numbers of external particles do indeed grow like n factorial. Okay, so for the next few minutes, I'm going to simply try and verify this factorial growth of amplitudes, and the rest of the analysis is simple. Okay, so usually, at least in the textbook formulation of string theory that I learned, you formulate string amplitudes just as integrals for the positions of vertex operators in the round sphere. But in fact, you can of course think of string amplitudes as integrals over the moduli space of the punctured sphere, and then you can put the hyperbolic metric on this punctured sphere. This is slightly subtle because this Weyl transformation is singular, but it was worked out carefully many years ago by these people. And what I want to emphasize in this formula for the tree amplitude that you get if you formulate string amplitudes this way is that when you put this hyperbolic metric, the measure on moduli space that you get is what's called the Weyl-Peterson measure, which is the natural measure in the moduli spaces of Riemann surfaces. And then you get some functional determinants and some worldsheet correlation functions, as usual. So now the core of the argument is that, in fact, the amplitude at large n is dominated by the volume of the moduli space. This relies on some early arguments that were made by Gross and Perival, who are actually looking at the behavior of string scattering amplitudes, actually just at the partition function, at very high genus. And in this setup, they were able to argue that the partition function was dominated by the volume of moduli space. And our argument is a simple extension of that because we have to deal with these worldsheet correlation functions as well. But I should say that these arguments are not really rigorous. So there's some amount of hand waving that goes in here, and I'm happy to talk about that more. But there's a description of what the heuristics that go into this is. So this is not really a rigorous argument, although I think it's persuasive and probably correct. Now, one thing that has happened since the time these large G partition functions were studied is that mathematicians have actually devoted a lot of attention to the behavior of these Weil-Peterson volumes. So this is something that's attracted a fair amount of attention recently, and they have a lot of very nice results. So, for example, Zograf and Mirzakhani and others were able to show that if you keep n fixed and you take the genus G to be large, then this volume of moduli space grows like 2G plus n minus 3 factorial. And in fact, they're able to work out many terms, including, up to order 1 over G. So it's really a very, very, very nice result. And let me point out something that's of relevance. If you set n equal to 0 in this formula, and you take G to infinity, you obtain this famous 2G factorial growth of string amplitudes that's very important for non-perturbative effects in string theory. And you see it just drops out of this formula. In fact, we're interested in the other limit, where you have G equal to 0 and large n, and mathematicians have studied that limit as well. And the leading behavior, I'm dropping all the sub-leading terms, the leading asymptotic behavior is indeed that the volume of moduli space grows like n factorial. Okay? So you see that if you then are willing to accept that this volume of moduli space dominates the amplitude, then you see that the tree amplitude grows like n factorial, which was the result that we wanted to show. Okay? Of course, as I said, there's some hand waving involved, so you might want to check this. And so what I want to show you next is that you can check this result through an entirely independent numerical analysis of string scattering at large n. So in fact, at large n, the string scattering amplitude simplifies, and it simplifies because the integral over moduli space localizes to some set of saddle points. These saddle points were first studied by Gross and Monte because they wanted to study high energy string scattering. We actually have low energies, but because we have a large number of particles, it's possible to again argue that the moduli space integral localizes on these saddle points, and the equations that describe the positions of these saddle points are also precisely the scattering equations that have recently received a lot of attention because Cachaso, Hay, and Yuan showed that they were also relevant for scattering just in ordinary quantum field theories. And so these are equations that have been studied a lot. And one of the things that CHY were able to show is that the number of solutions to these scattering equations is exactly n minus 3 factorial. So it's a curious fact that in fact there is exactly one saddle point per unit volume of this Weil-Peterson moduli space. It's just a curious fact. I don't know what to make of it. There's no reason this had to be the case, but it is the case. And this is something that I think is nice to point out. Okay. But now that you have these saddle points, you can try and evaluate the amplitude using these saddle points. And so what we do is as follows. Of course, at large n, because there are n minus 3 factorial saddle points, we can't evaluate all saddle points, but we can evaluate some random sample of them. So this is like a Monte Carlo sample of these saddle points. And then you evaluate the string integrand at these samples, and then you take the mean that you get for, over these randomly sampled saddle points, and you multiply it by the number of saddle points, which you know very well. I should say there's a note of caution here as well. You see, this kind of random sampling might miss the case where there are a small number of saddle points which give you a very large contribution, but they're restricted to some very small volume of moduli space. So if you're trying to sample uniformly on the moduli space, you might miss these saddle points. And so, but that can only get us to underestimate the answer. So I think it's important that the way to interpret the results that follow is that they give you a very good lower bound for the growth of string amplitudes, but it would be nice to understand if they're really exact results for the growth of string amplitudes. So what we did is we examined about 40 million solutions of these scattering equations, all the way from n equal to 4 to n equal to 100. This is a non-trivial computation. It takes about 8,000 hours of CPU time. So it's not something you can do on your desktop. But it's not a huge computation by the standards of people who do big numerical computations. So if you have a big cluster, then this is something that can be done in a couple of days. Okay, so it's a medium-sized computation. So let me show you what results we get. So here's the amplitude, and this is n on the x-axis. These dots are the data points that we have, and the solid line is a fit to factorial growth. Apart from the factorial growth, there's some subleading exponential growth and some constant that we are not interested in, because that's all subleading at large n. And the main point here is that with a coefficient of 1 in front of this factorial growth, these lines, by the way, the line on top is for lower energies, and the line below is for higher energies. You see that the string scattering amplitude obeys this factorial growth to really, really good approximation. So this is the answer for the type 2 superstring. You can also do this for the bosonic string, and once again you see that there's a really nice fit of the factorial growth to the data that we obtain. So I think the point I want to emphasize is that this numerical analysis lets you verify that this factorial growth is perhaps the correct answer for string scattering, but at least it gives you a very good lower bound for the behavior of string scattering amplitudes. And this is an entirely different argument from the previous argument I gave you based on the volume of moduli space. So based on these two arguments, we believe that it is true that string amplitudes grow factorially at large n, and then that tells you that there are these bounds on how large you can take n before string perturbation theory breaks down. Okay, so now in the last part, I want to describe briefly how this loss of locality that's suggested by this breakdown of string perturbation theory is precisely sufficient to resolve at least some versions of the information paradox. Okay, so let me remind you a little bit about how one goes about looking at some of these refinements of the information paradox. The key result is this result by Page and the average entropy of subsystems. And the way to interpret it in the black hole setup is to think of the von Neumann entropy of the radiation that's emitted from the black hole. And Page argued, and I think persuasively, that this von Neumann entropy, it starts at 0, because initially there's no Hawking radiation, and then it goes up, there's a lot of thermal Hawking radiation that's emitted, and then at some point of time, which is called the Page time, which is when the area of the black hole has reduced by a factor of 2, this curve turns down and it goes down all the way down to 0. So if you started with the pure state, you end up back with a state which has 0 von Neumann entropy, as you would expect from unitarity. And the way this latter part of the curve is interpreted is by stating that information starts to exit the black hole after about half the black hole has evaporated. Okay? So that's the statement that I want you to keep in mind. Okay, so now if you believe this statement, then you immediately run up against what's called the cloning paradox. So the cloning paradox goes as follows. Imagine some black hole that was formed from the collapse of a pure state. So this is an example of Vaidya collapse, where some black hole is formed. And then this black hole evaporates, and eventually it completely evaporates away. And then you can draw this extended Penrose diagram. But if you look at the geometry closely, you see you can also draw these nice slices on this extended Penrose diagram. These are slices that have low curvature everywhere, that also stay well away from the singularity, but they have the property that they intersect the infalling matter, and they also capture a significant fraction of the outgoing Hawking radiation. You can make them capture as much as you like by tilting them up more and more. And now you see that I said that the information exits the black hole in the Hawking radiation. So you see this nice slice captures the Hawking radiation, so the information about the infalling matter is here, but this nice slice also intersects the infalling matter, so the same information is also here. And so it looks like the same information is now present in two different parts of space-time, and this is what is called the cloning paradox, because it seems like you took some information here and you duplicated it, and this is of course in clear contradiction with the linearity of quantum mechanics. There is a closely related paradox. It was first pointed out by Mathur, and then AMPS did some more work on this, which is called the strong subadditivity paradox. And the strong subadditivity paradox goes as follows. Once again, you think of a black hole that was formed from collapse, but you look at it at very late times. You don't need the extended Penrose diagram. You just look at it at a time after the Page time. And here's another nice slice. And then you define three regions. You talk about the region far away, and I'll call that A. That's some region that's well away from the horizon. And you talk about the region close to the horizon, and you call that B. That's the orange region. And you talk about the region just behind the horizon, and I'll call that C. That's the blue region. Okay? But now the Page argument tells you that the new radiation in B is entangled with the old radiation that lives in A, but just an analysis of the Hawking process tells you that the new radiation, is also entangled with its partners, because the way Hawking, radiation works is you have pair creation. And therefore it looks like this B is entangled with A and also with C, and that violates the monogamy of entanglement, which can also be expressed in terms of the strong subadditivity of entropy, which is a general theorem about the von Neumann entropies of these three regions. So it looks like, once again, you have a contradiction if you believe Page's argument. Okay, so now the key, let me now try and describe how these non-local effects would resolve this. The key to making these paradoxes a little more precise is to think of how you would really measure them. You need to think of protocols to measure and detect these paradoxes. Now the main thing that makes it difficult for you to detect these paradoxes is the following very simple and general theorem in quantum statistical mechanics that tells you if you have a big Hilbert space of size e to the s, dimension e to the s, and you use the Haar measure on this Hilbert space, and you pick some state using the Haar measure on the Hilbert space, and then you measure some correlation function in that state you picked using the Haar measure randomly, then the answer you get is likely to be exponentially close to the answer in the microcanonical density matrix. Okay? But of course, the microcanonical density matrix, even if it gives you exponentially close answers for all these simple observables you're making, is of course very different, because if you look at the von Neumann entropy of the microcanonical density matrix, that's S. And of course, the von Neumann entropy of the pure state is 0. So if you want to if you want to really measure these paradoxes that have to do with measuring von Neumann entropies or extracting some scrambled information, you need to do something to beat this theorem. One way to beat the theorem, there's more than one way to beat the theorem, but one simple way to beat the theorem is just to measure e to the s different observables. And then you can beat this theorem and get something that lets you differentiate the microcanonical density matrix from a pure state. But it's not hard to persuade yourself that if you wanted to measure e to the s observables, then at least some of your observables have to be of order s point correlators in the Hawking radiation. This is just a counting problem, which is not hard to persuade yourself. Okay, but now these s point correlators correspond to s matrix elements with s insertions, and the energy of each insertion is a temperature T of the Hawking radiation. So now you could go back to this bound and perturbation theory that I described, and you could say, well, if you have particles of typical energy T, how many particles do you have to have before string perturbation theory breaks down? And surprise, surprise, the answer is that you have to have exactly n equal to s particles before string perturbation theory breaks down. So precisely at the threshold at which you might think that you're starting to see this paradox, string perturbation theory breaks down. And what this tells you is that these S matrix elements receive non-perturbative corrections and possibly also receive non-local effects. So if you believe that they receive non-local effects, then you see that these paradoxes can be resolved in a rather simple way. Because now the statement is just that you think of this cloning paradox, but really the claim is that this operator inside the black hole should be equated to a complicated operator outside the black hole, like we had in empty ADS. And if this is the case, it's clear that there's no cloning. All that's happening is when you make this measurement and this complicated measurement outside, you're really making the same measurement. It's not that information is cloned. So really what is lost is there's a subtle loss of locality, but no violation of the linearity of quantum mechanics. And the same resolution holds for the strong subadditivity paradox. You see, if it's true that you have polynomial constraints between these different regions, then of course the algebra of the theory doesn't factorize. You know, it's not just a question of putting things on the lattice. There's really fundamentally a lack of factorization of the algebra of the theory due to these polynomial constraints. And if the algebra of the theory doesn't factorize, then the strong subadditivity of entropy is inapplicable. So once again, you see how these subtle non-local effects can resolve this version of the information paradox rather easily. Some of you might not be persuaded by this. You might think this is too heuristic. So the last thing I want to do is I want to go back to my favorite example, which is empty ADS. And so let me just try and point out, and I'm out of time, how you can in fact set up these paradoxes in empty ADS as well. Okay? So this is a cross-section of just empty ADS, and in empty ADS, it's a constant T cross-section. I've set up a region which is near the boundary, which I call A, and some region deeper inside, which I call B, and some region that's even deeper inside, which I call C. But in empty ADS, I proved for you at the beginning of this talk a formula that said that operators in C could be written as complicated polynomials of operators in A. So this is not heuristic. This is something you can really show. But now you might say, oh, information in C also lives in A. You know, so in the same space-like slice, it looks like you have the information in two parts. So you have cloning. Or you might say, oh, this region B is entangled with C because these two are close by, but all the information in C is also present in A. So you have a violation of the monogamy of entanglement, or paradox. But of course, there's no paradox in empty ADS. It's clear that these paradoxes are resolved just through a subtle loss of locality, and the statement is really that all the information is in A, and the emergence of B and C is an approximate phenomena that happens when you don't look at the fine-grained observables that are required to measure these paradoxes. Okay, so I'm at the end of my talk. Let me just summarize. I said that in empty ADS, you could show these formulas using the Reeh-Schlieder theorem and the Hamiltonian is the boundary term that allowed you to write an operator at one point as a complicated polynomial of operators near the boundary. This relied on the Gauss law and a breakdown of 1 over n perturbation theory. And this gives you a motivation to study flat space string perturbation theory. And the claim was that if you took small e, large numbers of particles, then flat space string perturbation theory breaks down at least by the time you reach this value of n. And this is relevant for the black hole, because if you set E to be the Hawking temperature, then this value of n is precisely the entropy of the black hole. And therefore, it suggests an elegant resolution to some versions of the information paradox, namely the cloning and strong subadditivity paradoxes, through a subtle loss of locality for high point correlation functions. Thank you very much for your attention.
So I just want to make sure these relationships between operators,
Yes.
does it stem at all for something like a stringy exclusion principle? Like if there was a large n dual, you know that gauge invariant operators are not independent? Like
Maybe. I don't have something very intelligent to say. You're right, it sounds kind of vaguely similar. But I'd have to think about that more before I say something more about that. It does sound similar, and maybe I should think more about that.
Because the number which you needed for that was also related to n.
Yes, that's true. And so I agree that's an interesting thought. But I haven't thought about that. I don't have something more to say about that.
So I just wanted to make a comment about the use of the Reeh-Schlieder theorem. So of course forget about gravity, just do the Reeh-Schlieder theorem for quantum field theory in an ADS background. It's still true. But we wouldn't say that there's any subtle non-locality. It's just quantum field theory in an ADS background. So I think it's very important that gravity is involved in order to say that we need this non-locality. And in your Gauss thing, you do have that, right? So I think you're conflating two different things, right?
No, I thought I said that very clearly, in fact. Let me go back, just to point out that I said. Maybe you missed it. It's certainly true that the Reeh-Schlieder theorem would hold in any quantum field theory, in any local quantum field theory, and there's absolutely no violation of locality in the Reeh-Schlieder theorem, absolutely none. And what's important is here, it's the fact that you can write down the vacuum projector, and that's what lets you construct this formula. And the vacuum projector you can write down in terms of boundary operators only in a theory of gravity. And so I completely agree it's very important that gravity is involved, because in any other quantum field theory, the Reeh-Schlieder theorem holds, but of course there is no violation of locality. This is critically dependent on this fact that you can construct the vacuum projector and gravity as a boundary term.
Yeah, okay, thanks.
So this formula that you have here, and
Yes.
that you had in the first part, I mean, this is valid just within semi-classical gravity, right? So you're writing an operator at the center in terms of operators far away. So can you violate locality in this way? Can you send a signal
I'm sorry, I can't.
using this operator?
Well, you could send so you'd have to act with this complicated polynomial. So you'd need a super observer to do that, because the observer has to act with order n, order n insertions. So you can ask if a bulk observer can do that or not. But if a bulk observer can act with n insertions near the boundary, or if you have some boundary super observer who acts with n insertions near the boundary, then yes, this observer could immediately hit somebody who was in the center with something. This is not surprising. If you're an all-powerful observer who lives in the boundary, and there's some little bulk observer who's living in the middle of ADS, you can act with a unitary that will hit him immediately. It's just a precursor statement. So yes,
Right.
you could.
But could we actually do that if we surround someone? Can
we actually do that?
into a super observer? Could we hit them in a way that violates causality?
Well, I mean, you have to act with order n insertions. So you could ask, for example, for the sun. If you tried to ask what S would be, and you tried to do this with somebody who was near the sun, you would have to act with 10 to the 77 insertions in some region around the sun. So yes, if you could, yeah. I mean, I don't know if you're asking a practical question or not. Theoretically, yes. In principle, yes. Of course, we could do it.
One more question. Dieter.
Ago, we did a very similar calculation, and we also computed the scattering amplitude of 2 gravitons into n gravitons.
Yes.
And also using the scattering equation, we got this factorial growth of the amplitude, and at the end we also concluded that something special is happening when n equals s or n equals e. So is your calculation somehow different from ours?
Yes.
Or?
It's a little bit different for two reasons. I should have mentioned it. I'm sorry. Thank you for pointing out. I should have mentioned it. It's a little bit different for two reasons. First of all, we don't consider 2 to n scattering because we don't want any of the particles to be ultra-Planckian. So we consider n by 2 to n by 2 scattering. But that's a minor point. I think the other difference with your calculation is, if I understand correctly, when you use the solutions of the scattering equations, you had special kinematic points. So you had to take special kinematic invariants, and then you were able to find an exact solution to these scattering equations. We are actually a generic point. So in fact, we pick these points randomly in the kinematic space. So that's one important difference between your calculation and us. But I should have mentioned, yes, it's true. Yes. Sure.
Also rather generic in the sense that we only assume that the energies of the outgoing particles are small.
Yes, that's true, but I think there's a difference actually between the bound you found and the bound we found, because I think the growth is different at these special points in kinematic space. So we can discuss that more.
Okay, I'm looking at your formula, how many particles you need.
Yes.
Obviously, a big planet or a star will exceed it. So if I have a distant star and n plus first observable around here, it looks like that star is going to non-locally influence what happens here, and I'm trying to figure out how that works.
I think it's related to something that Douglas said in his talk. A bucket of water is chaotic, but that doesn't mean if you poke a bucket of water, it explodes. So the effective field theory tells you that these non-localities that you have at high point functions don't leak down to lower point functions. So everything we measure is a low point function. And it's true that if you measured a connected endpoint correlator, you would see all sorts of complicated effects, but they don't leak down. It's very important that they don't leak down to low point observables that we could measure.
Okay, thank you.
If it's very short.
Yeah, also for conventional quantum field series, like phi to the 4,
yes.
for processes with a large number of particles,
yes.
perturbation theory breaks
yes.
down due to combinatorial number
yes.
of diagrams. So
yes.
is there a difference?
This is what Rubekov showed, and in fact, our analysis was indeed influenced by what Rubekov showed. There's no difference there are a couple of differences, by the way. The kinematic factors, the precise bound that you get works out slightly differently. The bound there is n is proportional to 1 over root lambda in 4 dimensions. You don't get these powers of energy, but that's just a statement that the coupling constant in phi to the 4 is lambda, whereas the coupling constant here is E by Planck. But there's one important difference. You see, the breakdown of perturbation theory in phi to the 4 is not a big deal, because, phi to the 4 may not be well defined, but in some other theory that's well defined, you just go to a lattice and you compute some non-perturbative things. The breakdown of perturbation theory in gravity is special, because locality in gravity makes sense only in a perturbative sense. Only when you're about a saddle point of the path integral. If you can't compute something within a saddle point approximation, then locality may not make sense. So locality in gravity, the breakdown of perturbation theory in gravity has some significance for the loss of locality. But the mathematics of the breakdown of perturbation theory is similar in ordinary quantum field theories and in gravity.
Yeah, but actually there Valery showed exactly that instead of going to the lattice, one can semi-classically, there are some semi-classical methods to resum and calculate this to end processes. It looks like Schwarzschild background doing exactly that for us in gravity. It's a semi-classical background, and we calculate Hawking evaporation, and we see.
So let me say, this is, I thought that those semi-classical things were done at, again, very special, very simple regions in kinematic space, almost in matrix model calculations. But let me say one more thing. What I want to think about here is that you form the Schwarzschild black hole, and then you're trying to measure some very high point correlator at Scri plus. And I'm claiming that the saddle point you need to use for that very high point correlator is not the same saddle point that you'd need to use to measure a 2-point correlator at Scri plus.
Okay, maybe we should stop the discussion. One more question. Okay, thank you. Thank you again.